Hello and welcome to today's lecture. We are today going to talk about colorings of graphs again, but now from a different perspective. So last time we were concerned with whether or not you could color the vertices of a certain graph in a certain number of colors in such a way that no vertices of the same color were adjacent. So suppose it's possible, then it's in general possible in many different ways. And that is what we're going to look at today. So we're going to look at the number of ways that you can color a given graph in a certain number of colors. So the notation that we will use will be this, Pg of k. So Pg of k is the number of ways a graph can be colored, meaning in the sense of vertices, using k colors in such a way that no adjacent vertices have the same color. So let's look at a couple of examples. Let's look at this graph. So if this is our G, then we might ask, what is PG2? So this is the number of colorings using two different colors of the graph G. Well, this is not going to be possible because all the vertices are adjacent. As we noticed last time, this graph is not two colorable, so this is simply going to be 0. Then you might ask, how many ways can I color this graph in 3 colors? And that is going to be possible. We have at least one way, namely color this green, color this red, and color this blue. And in this case, all the vertices have to have different colors because they are adjacent to each other. And so all we can do is throw these colors around. So maybe A is blue, C is red, and B is green, and so on. And so we get all the possible permutations of 3, which is, as you can check, 6. So green, red, blue, green, blue, red, and so on for each vertex. You can check that the number of permutations of 3, this is exactly 3 factorial, which is 6. So this was this special case. Let's look at this next case that's a bit easier. So this is our graph G. And now I wonder, how many times can I color this graph G in 7 different colors? So pause and think. Okay, so if I have 7 different colors, how am I going to approach this? I need to color the first vertex somehow. So I have 7 choices of color for this one. Once I have done that, that color is used. I cannot color this vertex with the same color because it's adjacent. So I have only 6 colors left. And so the total number, because of the principle of multiplication, is 7 times 6, which is 42. An altogether nice number. So a few things to notice about this coloring business. First of all, as you saw in the second example, we don't need to use all colors. If we have 7 colors to color a graph with 2 vertices, it's perfectly fine to just use 2. And this is in general. So when we mean number of ways to color in this many colors, we mean in at most this many colors. Secondly, we always assume the vertices to be labeled in this count. So the coloring the first vertex red and the second vertex blue is not the same as coloring the first vertex blue and the second vertex red. We assume that we have labeled the vertices so that they are different. 1 and 2, I mean, they are different, but we don't identify these 2 things. So indeed, there are 2 colorings with 2 colors because you choose whichever color you want for the first, red or blue, and then the second has no choice. Another thing that you saw in this example is that being k colorable means precisely that this number is positive. It's not 0. And the chromatic number Remember, that was the smallest number of colors that you can use to color a graph. It's going to be the smallest k such that pg of k is greater than 0. The smallest k with a positive number of colorings of the graph we are looking at. Okay, so now let us step up our game a bit and look at a bit more complicated graphs and also a more general question. So now we want to find out pg of a general k. So for any k. In the last example we had k equals 2 or k equals 7. Now we want a general k. The principle is exactly the same, but now we have to be a bit more systematic and careful. So let's look at this graph, for example. And I have next to me my color box with k different colors that I'm allowed to use. So let's start with this vertex. Why not? This vertex can be colored in any k color, because so far we haven't colored the other vertices. Now, this vertex can be colored with k-1 colors, because I'm allowed to use all colors except the one I used for the adjacent vertex. Same with this vertex. It's only adjacent to my first vertex, so I am allowed to use my second color, but not the first one. So k-1. And for this vertex, same principle, k-1. So the answer is k times k-1 to the power 3 by multiplying all the possibilities. Now you might wonder, why did I start with this vertex? What would have happened if I had started with a different one? Well, I would have gotten, not surprisingly, the same thing. At least I hope I get the same thing, because otherwise my method is wrong. It shouldn't matter which vertex I start coloring if this is a well-defined notion. So let's start here. Assume I start with this vertex and now I can use any of my k colors for this one. That leaves me with k-1 options for this one. For this one, I'm allowed to use my first color again, but none of the colors I used for this one. So it's still going to be k-1. And here as well, the only forbidden color is this one color. So I have k-1 colors left. And again, I get k times k-1 to the power 3. So the point is, once you have put a color, the real choices only depend on, once you have picked a vertex, the real choices only depend on what vertices are adjacent to it. So this was k to take k times k-1 to the power 3. Let's look at a different example. The for complete graph. So again, the first vertex I start with always allows k colors. Now this vertex has k-1 colors available because I am already using one color. This vertex is adjacent to both of these. So now this color is forbidden and this color is forbidden, and they must be different because they were adjacent. So I have k-2 vertices. And this one is adjacent to 3 vertices. And I know that these 3 vertices can be colored by have to be colored by 3 different colors because they are all adjacent to each other. So I'm sure that exactly 3 colors are forbidden, and I have k-3 options here. So this is k times k-1 times k-2 times k-3. So if, for example, k was 17, then I will have 17 times 16 times 15 times 14 possibilities. If k were 2, then this k-2 would be 0, and that would automatically make everything 0, which makes sense because I cannot color k4 with 2 colors. So another example, a trivial example, but one that we will come back to several times, is the null graph. So the null graph on n vertices can be colored with k to the power n colors because I can color each vertex however I want. There are no edges, so there are no conditions on the colors. As an exercise, show that if you have a tree, then the number of colors is k times the number of colorings using k colors is k times k minus 1 to the power n minus 1. Remember, for this particular tree, this is correct. We had this number of colorings, and prove this in general using a general method. Another exercise, prove that for the complete graph, the number of colorings with k colors is k times k minus 1 times k minus 2 times k minus 3, etc., all the way to k minus number of edges minus 1. So remember, for this one guy, we had k times k minus 1 times k minus 2 times k minus 3. So maybe use a similar strategy for the general complete graph.